Dark matter.
Dark matter.
Dark matter.
Dark matter.
Dark matter. Dark matter.
Dark matter. My name is Christy Hobley, and I'm interested in answering the biggest questions that physicists today have about our known universe. The best description we currently have of our universe is a model called lambda CDM. Lambda was found in Einstein's equations and is called the cosmological constant. It's currently theorized to represent an entity we call dark energy. CDM is the acronym for cold dark matter, as opposed to its theoretical partner, hot dark matter. Cold dark matter is thought to make up 99% or more of the entity which we call dark matter. Dark matter and dark energy, the two components of lambda CDM, are thought to make up over 95.5% of our known universe, but we just don't know anything about them. I talked to India Friswell for a good perspective on how to think about these two entities as interacting in our universe.
I don't know how you think about dark matter and dark energy, but I like to think of it as two like evil, or not two evil twins, like two brothers making a puzzle. And so dark matter is trying to build the puzzle, bring all the pieces together and build the structure of the puzzle, whereas dark energy is like taking the puzzle pieces, then running away. And so dark matter has to run, get the puzzle piece, then put it back. And like as time goes on in the universe, dark matter keeps running them further and further and further away, and that's exactly what's happening in the universe. So dark matter provides the gravity for all our structures to form, like the clusters, the filaments. If you've ever seen maps of the large-scale structure of our universe, it kind of looks like a huge spider's web in 3D. Whereas dark energy is this energy providing this kind of outward expansion, and so it's slowing down this structure formation.
So dark matter and dark energy make up a huge proportion of our known universe. But where did these ideas come from?
So I think it was about the 1860s or so. Astronomers were looking at the motions of the stars, and they essentially started to see that the stars didn't obey the laws of Newton as would be expected, given the number of stars that we could see were out there, making some assumptions about typical mass of a star. So one of the most interesting early contributions seemed to come from Lord Kelvin, which is a nice link to Scotland up here. Essentially, it's just a case of looking at the movements of stars and trying to understand how that fits in with the Newton's laws as we know and love them, and it doesn't quite work. So even back in the late 19th century, people were realising there must be more stuff out there than we can see, and we couldn't see it, so it became known as dark matter. I guess the reason why Zwicky starts to be seen as the father of dark matter is partly because of the character of Zwicky, which is an outstanding, interesting, controversial figure, kind of a personal anti-hero, but also because that was the era where things started to be quantified much better, so that it wasn't just supposition and sort of all things don't work so well. It was really, these are the specific numbers that we need to get to work, and this is how much of this dark material there might be. And then, again, partly because of who Zwicky was, that observation that led to the hypothesis of there being dark matter kind of then fell out of favour until the 50s and then 60s especially, where rotation curves were being measured by Vera Rubin and Ken Ford and several others as well. And again, that then provided even more robust data that suggested there was this extra stuff out there.
So the main hypothesis for us is that dark matter is a new type of particle. And again, we might be wrong. Okay, but let's call that a working hypothesis. Now, the standard model is extremely successful at explaining physics in terms of elementary particles. Okay, we know, for example, that the building blocks of our universe and everything that we're made of are leptons and quarks, so electrons, for example, and the quarks that make up protons, neutrons, etc. We've also discovered neutrinos, and we also understand forces, the fundamental forces, as the interchange of also fundamental particles. We've got the Z and W bosons and the recently discovered Higgs boson. Now, none of the known particles and none of the particles that we've been able to describe within the standard model can be the dark matter. We're looking for a particle that is neutral, that is stable on cosmological scales, that it hasn't decayed yet. And therefore that means that we have to invent something and we have to put it into the structure of the standard model.
So, for more than one reason, dark matter theoretically needs to exist. But how would we go looking for something that you can't see?
From the experimentalist side, we can also ask, how do we even think about measuring dark matter if it's dark? So there are different kinds of tests that are devised, and they can be divided up into things called direct measurements, indirect measurements, astronomical, and collider. So the idea is that dark matter is hypothesized maybe as some kind of a particle. We don't know what, but let's suppose it's some kind of particles that are floating around in the universe. I can talk a little bit about that after this. So suppose these particles are wishing through, going past the Earth or something like that. So one of the ideas of experiments is that, well, let's suppose that we put some other particles that we can measure, like heavy elements, right, into a big cavity, and let's just let them sit there, and if they start jiggling around, then something clearly had to gone through. And we know certain things that can cause this motion, like light and radiation and everything like that. So experimentalists try to control all those kinds of backgrounds. In other words, they go deep underground where there's going to be less radiation, etc. So they try to control all of these parameters, and so then if they start seeing motion, it might suggest that some kind of an unknown particle has actually struck one of these heavy nuclei, and that might give us a hint on sort of the flux of dark matter that's going through.
And so that's what I do. I work on experiments with a couple of hundred other people from around the world, lots in the UK, many more in the US, and then also Russia, Portugal, and South Korea, on experiments like Lux Zeppelin, which is a large liquid xenon-based detector. And it's essentially a large bucket of liquid xenon. And if these dark matter particles, these WIMP particles, are going through it, and one does bounce off a xenon atom, it will produce a big splash of light and some electrons that we'll try and detect.
Huge experiments like Lux Zeppelin, or LZ, have a lot of hope of finding dark matter particles in the future, if they do exist. But it's not the only approach to looking for them. Here we head to Bowlby Mine to find out about a different way of thinking about the problem.
I work on an experiment called DRIFT. DRIFT stands for Directional Recoil Information from Tracks. DRIFT's a bit unusual in the search for dark matter. It's not like LZ or some of the bigger scale dark matter detectors out there. It uses completely different technology, and it's almost a different approach entirely to looking for dark matter. DRIFT, unlike the majority of dark matter detectors, is a directional dark matter detector. So, simply put, that means that when we see an event inside of DRIFT, when DRIFT detects something, it doesn't just find it as like a point particle, it doesn't give it just immediate information. It also collates a track, if you will. So instead of being a point event, you get a couple of millimeters track depending on the energy of the particle. And from this track you can infer the direction from which the particle came, so the origin of the particle, if you will. And this is really useful when searching for dark matter in particular. And so due to the way that we, as Earth, move through our galaxy, through the universe, we don't expect to be moving with the dark matter that surrounds us. We think that dark matter is kind of like ambient air. It does have motion, but it doesn't really move with us. It's just ambient, and we move through it. So, relatively speaking, if we're moving through something that's ambient, in our reference frame, that ambient thing, in this case dark matter, would be relatively moving towards us like a wind. So we call this phenomenon the WIMP wind. We suspect that as we're moving through the universe, we should be experiencing this WIMP wind as we traverse our path. And this is where the directionality of drift comes in. So drift aims to map out all the particles that it finds while it's running. What you can do with that information is you can plot it, those galactic coordinates of each event, onto the night sky. So for each event that you find, you pinpoint it almost to a picture of the night sky, let's say. And if dark matter does exist, and we find a number of dark matter interactions, they should all be coming from the same direction, because they're all part of this wind. We're all moving through them in the same direction. And if you look at the night sky, it should be in the the direction of the constellation Cygnus. So no other particle would give us this behavior. Neutrinos or neutrons, the full plethora of background that's available, they would all either move with us or have random motion. Nothing would act like dark matter. It's totally separate due to its characteristics. Or we suspect that's the case. And so if we did see a hotspot in the sky due to a number of events all coming from the same location, we can almost completely say that it's confirmed that dark matter exists. So that's why we run drift.
There's indirect measurements. We can look for annihilation. So dark matter is a particle, and as with particles, sometimes they can transmute into other things. Like if you have an electron and a positron, and they hit each other, then they will turn into light. Okay, it's a matter and antimatter type of thing. So in general, in particle physics, we can have phenomenon like that, and it's the similar story with dark matter. And it's possible that through some interactions, the dark matter can turn into other kinds of particles. And theorists have done various calculations, and there's predictions that dark matter in certain kinds of astrophysical phenomenon would produce abundances or higher levels of antiprotons or positrons and things like that. So these are indirect measurements that we try to do. We put up satellites, or we do ground-based measurements of the X-ray spectrum and all these other different spectra in the universe, and try to see these sorts of excesses. Once in a while, there's kinds of blips that, this looks interesting, but usually everything can be explained by standard astronomy, by standard cosmology.
The third way of looking for dark matter through experiment is astronomical observations. Here I go to the Royal Observatory of Edinburgh to speak to Professor Joe Zuntz about how lensing can be used as a technique to find out more about dark matter.
So what we try and do most of all is look at lensing. That's my particular area, is looking at gravitational lensing. So if you throw a ball in the air, it will come down again. And that it starts off going in a straight line, but then gravity pulls it and bends it down towards the ground again. So we're used to the idea of gravity curving the paths of objects. What may be less obvious is it also curves the path of light. So if you shine a laser beam up into the sky, it will actually be bent very, very, very slightly downwards towards the Earth. Now that's far too small to see with the naked eye. You can't see that by eye. And it's too small an effect that you can't see it absolutely in except in the most extreme circumstances. So this was first detected about 100 years ago by Arthur Eddington, who was this fantastic early 20th century astronomer, very, very interesting man, did lots of really cool experiments. And he went to the island of Sao Tome and Principe, which is off West Africa, during a solar eclipse. And the reason he wanted to do this was that the only thing powerful enough to bend light that we could see it was the sun. That's the only thing with enough gravity to actually do this. In general, though, it's a bad idea to point your telescope at the sun, because you will melt your eyes. So you have to go there the only time you can do that, which is during a solar eclipse. So he found a solar eclipse and he looked at stars around the sun, and he saw that their apparent position was bent and moved by the sun's gravity during that period. And that was one of the experiments that led to us believing Einstein's theory of general relativity. So that's our current and best theory of gravity. So our whole understanding of gravity is built on this observation, which is a very powerful one.
So the theory and ideas behind lensing are actually quite old. However, they may be in a lot of use today. I spoke to Dr. Alex Amon on her upcoming projects using a technique called weak gravitational lensing.
So I study dark matter using a tool called weak gravitational lensing. So as part of a team, we observe distant galaxies using our telescope in Chile. And between us and those distant galaxies is the cosmic web of the universe. So the universe has a web-like structure made of dark matter, and the dark matter is in clumps in the universe. The dark matter is massive, so it has gravity, and that gravity warps the fabric of the universe, which we call space-time. So the space-time gets curved. Now, because of that, when we observe distant galaxies, the light no longer travels in a straight line. It also gets curved due to the presence of the dark matter and the gravity of the dark matter. So that means that when we take pictures of galaxies that are far away, their light, because of the bending of their light path, the galaxy images appear distorted. So the galaxies are a little bit more elliptical than they really are. Now we can, by measuring this distortion, by measuring this lensing effect, we can understand by measuring this distortion effect, we can understand about the stuff that the light passed through. So we can understand the properties of dark matter.
Direct observation is only one way of looking for dark matter. through the skies. Another way is to use simulations to try and replicate what we currently see. And then obviously, if the simulations replicate Earth and universes like ours, then potentially the inputs to that simulation, in terms of dark matter, are potentially correct. This simulation simulates what the universe would have looked like in a very, very early snapshot of time, where you can see matter being drawn together into structures. It's important to note, however, that the involvement of dark energy is not represented in this simulation, as the viewpoint sort of zooms out in all directions at the exact same rate as dark energy would spread the particles apart.
As gravity gets to work, you'll see not only small, tight, spherical blobs of matter congeal, but they themselves form aligned structures. So you'll see large filaments of dark matter, and you can see such filaments in the distribution of galaxies today. So just visually, but also in terms of the quantitative statistics that you can measure, these simulations really make a very good match to the universe as we observe it. So on the really large scales, hundreds of millions of light years across, there's very little doubt that we know truly how much matter there is, and that the structures within it, which are mimicked today by the structures and distribution of galaxies, are a result of gravitational instability. So what a lot of people in the field are trying to do is to go beyond that and say, well, how can we use this information to tease out what the physical nature of the dark matter may be? And for that you've got to go to smaller scales, because as I said, if you go to large enough scales in the universe, even ordinary matter, gas will fall together in much the same way as the dark matter. In fact, the dark matter and the gas don't really separate until you get down to the sort of scales of individual galaxies like the Milky Way. So the hope is that by trying to simulate not so much the large-scale structure of the universe, but perhaps the formation of a single galaxy like the Milky Way, or even, most interestingly for some applications, the smaller dwarf galaxies. So the Milky Way has satellites that are a few percent of its mass, called the Magellanic Clouds. And so these little dwarf galaxies are the smallest things we know of in the universe, and those smallest units could reveal a lot about the nature of dark matter.
And finally, and maybe the best test of all, the acid test, I would say, would be collider, which is to actually produce a dark matter particle in collider experiments.
Finding a concrete dark matter particle or producing one in a collider would be a pretty compelling piece of evidence for the lambda CDM case. So I spoke to Professor Christos Leonidopoulos, who works at CERN and in projects like ACLAS, about how you might go about creating a dark matter particle inside a collider.
You would be looking for a collision where you have two very energetic protons collide and then nothing comes out. Or maybe something comes out one direction, but there's some imbalance because you've created something that's invisible in the same way that you would see in a galaxy a dark area, and you see that, you think that this is something that does not give you light, so it becomes invisible. So you're looking for collisions where there is a strong imbalance. You have some particles going one direction, but nothing on the other half of the detector, which looks very impressive as an experimental sequencer. And you say that, okay, I need to collect loads of those to understand if this is something that is maybe explained by the standard model, or I find some very large number of those asymmetric collisions that would point to dark matter, for example. One of the things that we're trying to do right now is you have the experiment, you have two proton beams that collide against each other at a very, very high rate. So you have 1 billion collisions per second. And you don't have the means, you don't have the resources to store every single one of those collisions. You have a system which is called a trigger, which is a combination of hardware and software, some advanced algorithms that in real time trying to make an educated guess on whether a particular collision looks interesting enough and has to be stored for offline analysis, or it looks very normal, very boring and should be thrown away. So the output of this process is what we store, and it's a very small fraction. So out of 1 billion collisions per second, we stored only 1,000. So it's a highly selective process, okay? We store what we think is the most interesting, potentially interesting collision events that could contain evidence for new physics or contain Higgs bosons that we want to study in more detail and all that.
At this point, it is fair to remind yourself that we have been looking for years and years for these type of events at CERN, and we still haven't found anything. And the trigger is ignoring billions and billions of collisions. So what are the odds that your trigger is simply systematically ignoring something that you would like to record?
So one of the, there's an ongoing effort, and this is something actually we're working on, and other people are working on this, is to try to deploy a more sophisticated suite of algorithms, including machine learning, into the trigger. So even if you cannot afford to increase the output rate of the trigger, maybe if you have some machine learning, it will be able to look into the events that you throw out and look for some anomalies. Maybe, hey, you think this is boring, but I see something that does not really make sense. Why don't we save this? Or let's try to collect several of those to see if we find a pattern that your baseline selection was going to throw away.
So we have these 4 different experimental methods of looking for dark matter. But where do we go next? I speak to a phenomenologist about the process of moving from experimentation to results and theory.
The way we understand phenomenology in particle physics is the bridge between theory and experiment. So again, is this dialogue of theorists having ideas that have to be tested, finding ways in which your new theories can give observable phenomena, and also reacting to experimental results. At the moment, the experiment that I work in, Super CDMS, and other experiments which are based on liquid xenon, I would say that we are the best at not finding dark matter. And this is actually very useful information as well, because it tells us physicists or theorists that many of the models that we were working with are either not correct or they have to be revised.
So we have our results, or lack thereof. And where do we go from there? We go to the observatory, where I speak to an astronomer about what their results and their data have told them about the search for dark matter.
It's also true that what we have seen is that the more data we have collected in the last 10, 20 years, what happened there is that we have been pushing all these dark matter particle models to higher and higher energies, and that always means that we are pushing our models to, or we are pushing dark matter models to regimes where dark matter behaves closer and closer to a perfect fluid. So that's what's been going on. Mm-hmm. You know, the more we work on it, the closer dark matter behaves to the perfect fluid, and that's what general relativity assumes, right? There is no quantum physics in general relativity. So everything we've been finding so far is that general relativity behaves extremely well. I mean, that as a theory, it's extremely interesting. I don't know whether quantum physics, I'm not an expert in the field, I don't know whether they can say something like that.
So after astronomy, I look in the opposite direction, to particle physics, where there are 4 possible candidates for what dark matter could be.
So let me just discuss briefly some of the kinds of dark matter particles that theorists have cooked up. So the one dark matter particle that's actually known to exist is the neutrino. Okay, so the neutrino is a very light particle. It interacts with almost nothing. Through measurements of beta decay and neutrino oscillations, we can put a bound that the mass of a neutrino is incredibly tiny, smaller than an electron volt. So an electron itself, electron volt is a unit of energy or mass. So like an electron is 500,000 electron volts. So that gives you an idea of how light the neutrino is. At the same time, the neutrino interacts with almost nothing. So it's an ideal dark matter candidate, you would think. But if you actually understand the history of the time history of the universe, of the neutrino in the universe, it used to interact to a degree in the early universe, and it was light, and therefore it actually was a form of hot dark matter. And I've already mentioned that in simulations, etc., we see that hot dark matter really doesn't explain the kinds of astronomical data that we see. So we can put a bound that, neutrinos can be a part of the mix, but it would be less than 1% of the dark matter that we actually need. So that's one candidate that we know of, but it really doesn't work too well. So then there's a whole slew of other possible candidates, and I should say from the onset that none of them have been observed, but there's a lot of theory that's been developed for all of them. So one of the promising candidates is the axion. That's another kind of particle. So there are problems in the standard model with the strong sector, the strong force. That's the force that binds protons and neutrons together. Okay. So there are certain symmetries that the axion helps to restore called charge and parity. And so that's the theoretical motivation for the axion. But it also turns out that if you follow this route of trying to ensure some symmetries in the strong sector, it turns out that the particle that you actually create turns out to be very light, and it turns out to be very weakly interacting. Now, although the axion is light, it's so weakly interacting that it never actually interacts with anything, even in the early universe. And that's why it actually is not relativistic, so it's a form of cold dark matter. So, as I mentioned, cold dark matter is exactly the kind of dark matter that we want. So, in that respect, the axion is a very promising candidate. But only in that respect, because, as I said, many attempts to observe it, there's been nothing. So, another candidate is called the neutralino. So I mentioned that we're trying to build theories beyond the standard model, and so one of the most elegant ideas is an idea called supersymmetry. So supersymmetry, in simple terms, is an attempt to unify the forces and the particles. Okay, and the consequences of trying to build a supersymmetric theory is that you actually, in a sense, double the number of particles in the universe. At least that's your prediction. And the lightest of these particles, of the new supersymmetric particles that you create, the theory tells you that this particle will be absolutely stable. And now that's a very important requirement for a dark matter candidate, because dark matter has to exist on cosmological scales, time scales. So the thing called the lightest supersymmetric particle, the neutralino, is a very interesting theoretical candidate for dark matter. The other interesting thing is that a lot about supersymmetry are things that are real predictions that you can test in colliders. And there were a lot of predictions made about supersymmetry for the LHC, and so far nothing has been found. And the neutralino was certainly one of the candidates that was hoped could be seen in the LHC, or maybe it'll be in a future collider at a higher energy scale. So the thing about the neutralino is that it's fairly heavy. It's about, there's a mass range on it. I mean, we don't know the exact value, but it has to be certainly heavier, quite a bit heavier than a proton, maybe 100 times heavier, maybe 1,000 times heavier. So it's quite a heavy particle, but at the same time, it's very weakly interacting. And it's actually part of a class of particles called weakly interacting massive particles, or WIMPs, as we like to call them. So WIMPs have other nice qualities. If you actually look, if you look at the thermodynamic history of the universe, okay, so what we understand is the universe is expanding. So that means if you go back in time, it would be contracting. So all that matter would get into higher concentrations, and therefore the temperature of the universe would rise. If you go back to the very early phases of the universe, the temperature of the universe would be something like 1 billion kelvins or higher, okay, really high. And what happens is that all of the elementary particles, so what happens is that, for example, a hydrogen atom, right, it's a bound state of an electron and a proton, and there's a certain binding energy, okay? But when the temperature gets high enough, what happens is that there's enough energy that the electron can simply keep getting knocked out, okay, of its bound state, and it can just be free. And so what happens as temperature gets higher, for example, is that the first thing that happens is that these atoms, they completely get stripped away and they become a plasma. So the protons run free, the electrons run free. Then eventually the energy gets even higher and the proton itself gets ripped apart and all the quarks start running free. And as you get to higher and higher energies, basically all you have is a soup, just a plasma of all the elementary particles. Okay, so whatever is in your fundamental theory would just be floating around there. And these WIMPs, okay, we understand some things about the WIMP particles, that in the early universe they would have interacted, and they would have interacted a lot with the other particles. But when the temperature of the universe became below the mass of this particle, then it would become heavy, right? Because when the temperature is higher, that means that basically there's enough energy that the particle can move around. But once the temperature becomes below its mass, it becomes heavy, and then it stops interacting, and its kind of abundance then freezes at that point. So we can use the theory, such as the supersymmetric theory, and we can use our understanding of cosmology, and we can actually make estimates of what the abundance of WIMPs we should expect to find today. And the interesting thing is that we do find from this kind of theoretical estimate about a 10% abundance that should come about from a WIMP candidate. And remember that I said that dark matter is about 20% of the content. So within order of magnitude, I mean, a factor of 2 is fantastic for a cosmologist. So within orders of magnitude, WIMPs seem like an intriguing candidate. So, if you put the theoretical picture together, you have cosmology on one side saying, oh, I can predict a 10%, 20% abundance. You have particle physics saying, well, here's a really elegant extension of the standard model, and this dark matter candidate just sits right there, available in some sense for free if you want to accept supersymmetry. So you can see the motivation from a theorist point of view, and I emphasize from a theorist point of view that this would be a very intriguing candidate. So, a lot of interest has gone into trying to detect and understand neutralinos. But again, nothing's been detected. Another supersymmetric candidate is the gravitino. So the gravitino is the supersymmetric partner to the graviton. The graviton would be the particle associated with gravity. So that is an interesting candidate, but the problem is it's very weakly interacting, it's very light, there's very few other signatures. We couldn't possibly hope to find it in a collider, but as far as theoretically, this could be another candidate.
For a slightly broader perspective on the theory, I speak to one of Edinburgh's most famous theorists, Professor Peter Higgs, and where he thinks the future of theory is headed.
I mean, as somebody with an interest in sort of basic quantum field theory for particle physics, I'm really rather an enthusiast for so far unverified theories like supersymmetry, where there are candidates for dark matter already embedded in the theory, but unfortunately, as far as the big machine at CERN is concerned, no experimental evidence yet for it. So, I mean, as a theoretician, I don't really see how we can end up with a theory which unifies gravity with all the other forces without having supersymmetry. It's a mathematical framework which makes it possible in a way which was not previously possible. So where else do we go if supersymmetry is not right? I don't know.
If particles such as the ones found in supersymmetry theories are in fact wrong, all hope is not lost for the search of dark matter. Some physicists have come up with a very different way of thinking about the problem, and here I head to the observatory to hear more about it.
But yeah, there's a whole range of theories. One theory is maybe we've got the whole theory of gravity wrong in the first place. Our inference that there is dark energy out there comes from looking at gravitational systems. So looking at the universe and then saying, hey, we know the laws of gravity, so here's what's happening. Perhaps we just have those laws of gravity wrong. Maybe it's that we've misinterpreted what we're seeing because we're expecting them to behave under the gravity that we're used to seeing. That could be wrong. And there's lots of theories about how that could be wrong. So we've investigated a lot of these things. So we've said, well, what if gravity behaves differently in dense environments compared to empty environments? That might explain something. So that would be why we can be here on the Earth, and all the experiments we do are very consistent with our theories of gravity because we're in a dense environment with lots of matter around. But maybe out in the empty void regions of space where there's no matter, maybe the laws of gravity change in those situations. Maybe suddenly it just switches to a different kind of mode in those environments. And that's a strong possibility too that we're investigating right now. Perhaps these laws change in different contexts. And it's hard to write down a theory that sort of makes sense with what we do know, because we have very, very strong measurements of gravity in a few specific cases. So we know very well on the Earth and the solar system how well gravity works. We know exactly how it behaves because we have incredibly precise measurements. So any theory we come up with has to reduce to that in some situation, but not in others. So you're in a very delicate balancing act when writing down a mathematical theory of this stuff to something that works with what we know, but also explains the weird stuff.
Suggesting that Newton's fundamental laws of gravitation might be wrong may seem like an insane thing to do. However, completely revolutionising the way we thought is what made these people famous. So I spoke to a philosopher, Michela Massimi, on the process of completely revolutionising the way you think.
What happens in a specific historic period when the community has to take a decision and somehow decide whether to embrace Copernicus or not, or they embrace, lambda CDM or not, and what are the factors that in a way explains and justify the formation of scientific consensus around the theory over another. Those raises an interesting question, I think, from a philosophical point of view, because it's a question of looking not just at the evidence, but at how sometimes the evidence can be evidence for alternative hypotheses, and how those different alternative hypotheses can do different justice to the evidence in terms exactly of explaining versus accommodating versus evidence from experiment or evidence from computer simulation, and I think those are the sort of questions that philosophers obviously ask. So I don't know, I tend to think that obviously it's the job really of scientists to do the science, and I don't like to think of philosophers as the one that, prescribe or give normative constraints to what the scientists should do. But I do think that there are some questions. There are questions about the method, the models, the role of simulation, the nature of experimenting. There are genuinely philosophical questions. Those are questions that a working scientist just wouldn't consider as genuine scientific questions, because they are epistemological questions about human knowledge, how we form knowledge, how our knowledge evolves, and what counts as reliable knowledge. And so in that sense, I think philosophy of science has an important role to play for science, but simply because there are gaps in the normal picture that working scientists just don't have the time and don't have necessarily the skills or the resources to address. And so that's a space for philosophers of science, I think, to kind of chip in and provide their contribution.
So we have looked underground in experiments, around the LHC and up into the skies to try and find out what the nature of dark matter could be. The theories that come from this have ranged from exciting new particles, to a perfect fluid, to simply a mistake in our calculations. So how will we know for sure? What lies in the future of dark matter experiments? I speak to Dr. Alex Amon to find out what the future of sky surveys holds.
Yeah, so it's a really exciting time for lensing because there are 3 ongoing surveys, and they're all in healthy competition, but they are really just developmental work for the upcoming surveys. Now these upcoming ones will see first light in the next decade, and they will really provide answers for what dark matter is and where it is, and they'll really deliver high precision astrophysics. So there are 3 of them, and in tandem is where their power lies. So there's Euclid satellite. Now that will be launched into space, and so it will remove our worry about the effects of our atmosphere creating further distortions in our images. And there's also the LSST, so the Large Synoptic Survey Telescope. Now that one is also based in Chile, and it will survey the night sky every 3 nights, so it will just keep lapping around. And eventually, by stacking all the images, it will create one of the deepest, largest images of our universe. So surveys now will map a size of the sky that's about the size of our moon, for example, whereas LSST will do the entire southern hemisphere. So it really will provide groundbreaking changes for the field. And then also along with those, you'll have DESI, so the Dark Energy Spectroscopic Image. And this one, this survey is a bit different. So it takes spectroscopic images. So instead of it being optical images of galaxies, I think John will talk about this, but it will precisely, instead of it being optical images, it will take spectroscopic images, and that allows you to see not only exactly where the galaxy is, but how fast it's moving away from us. And when you have a combination of techniques, so weak gravitational lensing is super useful for understanding dark matter, but we're at the stage where if you use a combination of techniques and probes together for our analyses, they give a lot more informative results.
So the future of astronomy seems to be looking up, but how about direct detection?
So broaden the search for dark matter and have potentially an ecosystem of experiments. To borrow a phrase from someone else, it's we don't know what this stuff is. Dark matter candidates span 40 orders of magnitude in mass, so we need to be casting our net very wide, whilst also going deep for those where we think we've got the most chance of finding something at present, given technology and given the state of our knowledge. So things like a generation 3 dark matter detector needs to be built, especially if it can open up into sort of a rare event search observatory rather than just being WIMP only, and expanding to different types of dark matter, expand past that as well and do neutrino physics and rare event searches and make an observatory. I think that's a compelling case. But then at the same time, broaden, open up, look at lots of other theories that we can go after. But you've got to map that to UK expertise and experience as well. Right? You can't just say, this is a good idea, let's go try that. It'll take time to build up the skills to do that in many cases. But that's fine. That's what we do, experimentalists.
Now we go back to Professor Peter Higgs to talk about where physicists should look in the future for new physics beyond the Standard Model.
Neutrinos, I mean, to me, in terms of the experimental evidence on where theories in particle physics should go, neutrinos are very, very important because they can be accommodated within the Standard Model. But if you go back to the 1960s, when, say 1960, which was when Shelley-Glashow first formulated an SU2 cross U1 electroweak theory, it was on the assumption, based on what was known at the time, that neutrinos had no mass. Now, it's clear that that's wrong. So we can sort of stretch the Standard Model a bit, but it isn't very natural to have massive neutrinos in it. So I think the evidence on the neutrino spectrum and all the parameters of the masses and the mixing and all this sort of thing is very important. But unfortunately, the data come in very slowly. So you have to wait many years before you get the answer. But I think that's probably where the present Standard Model is going to be shaken up and the theoretical directions in particle physics redetermined.
As the future of science grows, so does the need to work together as a scientific community and collaborate. I speak to Dr. XinRan Liu, who's been working on a collaborative project like Zeppelin, on the need to work together as a scientific community, and potentially end up doing science as a planet rather than as countries.
Interestingly, right, so that's the scale, right? So as your dark matter particle gets smaller and smaller, your detector has to get much more massive to look for it. And as a result, you bring all these people together and you build these large collaborations. And it's actually a beautiful thing, right? I think these physics experiments, so many institutes, so many universities from so many countries all working together is all in the hope of finding something that may or may not exist is a pretty good moment in human history.
Probably, it's really one of the only things that actually unites countries.
Right, that's right.